Here we are again with another video, just following up on Rolle's theorem. We'll be talking about the mean value theorem. The mean value theorem, very similar to Rolle's theorem, but in fact it is a specific case um, thereof that theorem. If f is continuous on the closed interval ab, same as before, and differentiable in the open interval ab, same as before, then there exists a number c in ab such that f prime of c equals f of b minus f of a over b minus a. So whereas Rolle's theorem says that f prime of c equals 0 specifically, this says that f prime of c equals the change in y over the change in x. In other words, the slope between those 2 points. And it can be any number as opposed to Rolle's theorem where the slope is equal to 0. So perhaps I said it backwards in the beginning. Rolle's theorem is a specific case of the mean value theorem. Let's look at the diagram that we can have accompanying this one. So here is x, and here is y, and we have some a value and some b value, such that a gives us, let's put a point right there, a gives us f of a, of course, and b, they don't need to be equal now, gives us f of b. Now, of course, they can be equal, but then that'd be considered a Rolle's theorem there, which is a subset, specific case of mean value theorem. And let's say somewhere in here, at least one time, we'll make it a nice boring one, so that is just one time. There's our graph. The derivative at some point c is equal to f of b, so f of b minus f of a, all over b minus a. The change in y over the change in x. Well, that's nothing more than the slope of the secant line, right? The change in y, change in y, f of b minus f of a is right here, f of b minus f of a, all over b minus a, right? That's the slope of the secant line. Right, m sub secant. Whereas this is the slope of the tangent line. There is some tangent line in here at c that those two slopes are equal. Right there it is. There's our c value, such that f prime of c equals f of b minus f of a over b minus a. Now think about some applications, which we'll talk about later. But the main application one we'll discuss later is somebody's average velocity. Right, that would be your slope of the secant line, okay, the total distance traveled, f of b minus f of a, over the amount of time, b minus a, the average velocity, is equal to, at some point, your instantaneous velocity. That's what this is saying. Your average is equal to the instantaneous at some point, at least one point. Okay, and that should make sense. You can't achieve an average of, let's take test scores. You can't achieve an average of an 80 without achieving at least an 80 at some point. Now test scores are a little different because you could get an average of 80 without actually scoring an 80, right? You get a 75 and an 85 that average out to 80, but that's not a continuous function because you're talking integer values there and things of that nature. So that's not quite a good example there. But think about speed. If you're driving a car and you have an average speed of 50 miles an hour, say you start at 0, right? You're starting at 0 at some point. So in order to achieve that average of 50, you have to at least get to 50 at some point, and even above 50, because at some point your speed was below. And in order to get above, to cancel out the stuff that was below, you have to hit the point you're going to get to, the 50 there. Okay, so we'll talk about those applications of the mean value theorem and Rolle's theorem here shortly down the road. That was mean value theorem in a nutshell, where it says the derivative at some point is equal to the measure of the slope of the secant line at some point. Instantaneous velocity is equal to average velocity at some point, given a continuous function. Have a good one.